5 liters, and the cardiac rate, or you can say the heart rate. Okay, how many beats you'll have in 1 minute? It's called cardiac rate or heart rate. Number of beats per minute. How many times the heart pump blood in 1 minute? It's called cardiac rate, and that is around 75 beats per minute normally, but it can be increased or it can be reduced. So when there is change, homeostasis tries to maintain the constancy. Okay, that there is the respiratory rate, or you can say the breathing rate. How many times you breathe in and breathe out in 1 minute? It's called respiratory rate, and that should be 12 to 20. Okay, the normal, the set point, the physiological value. Okay, and the other secretion from endocrine glands. There are endocrine glands in the body, those secrete hormone, and those hormones released in the blood. Like for instance, one of the hormone is growth hormone, another is thyroid hormone, and so on. And each hormone in the body should have their normal value. Otherwise, when the hormone in the body is excess, or when the hormone in the body is less, result in different abnormalities. So secretion of hormones and the secretion of hormones in the body should be maintained constant. So this is another homostatically regulated variable. Rate of chemical reactions. There are a number of chemical reactions in the body, so those reactions should be normal, should be regulated. Okay, with our homeostasis. Okay, then in order to homeostasis perform its function, it needs components, and this is called the components of homeostasis control system. So there are 3 components. Okay, so the first component for our homeostasis is sensor, or you can say detector, or you can say receptor. So sensors are structures in our body, those sense the change. When your body temperature is changing from the normal, that should be detected. That should be sensed by our body, and these are sensors. So the sensors are structures in the body, those sense or detect the change. Okay, then after the sensors or the detectors sense the change, then what they do? They send a message or inform the integrators. So integrators are mainly the nervous system and the endocrine system. So integrators should be informed about the changed value in the body because of the sensors. Okay, so then what is the next step? Okay, the integrator compare the set point and the normal. Okay, the set point and the changed value. Like for instance, your normal body temperature is 37 degrees centigrade. Okay, and because of the changing factor, assume your body temperature is increased to 39, for instance. Okay, that is detected by the sensor. Then when the information or the message is getting to the integrator should ask or should compare the changed value and the normal value, because the integrator or the body knows that our body temperature is how much? 37 degrees centigrade. Now it is 39. Then there should be comparison. Okay, so integrators should compare the set point or the normal value and the changed value. So if there is change, command is made. Okay, command is made at the level of integrator, and that command is getting to the effectors. So effectors are structures in the body where appropriate response are made. Okay, appropriate response are made. Sorry. So look the figure. Look the figure at the right. This is example actually. Okay. Sorry, let me take back. Sorry. Okay. So assume your blood glucose level is increased. Okay. The stimulus rising your blood glucose level. Like for instance, if you eat carbohydrate meal or carbohydrate rich meal, like for instance, bread, for instance, assume, then your blood glucose level is increased. Okay. Then that increase in the blood glucose level from the normal should be detected by sensors in the pancreatic gland. Okay. So we have pancreatic gland, and in the pancreatic gland there are cells. Okay, like you can have the beta cell. So the beta cells detect increase in the blood glucose level, and the beta cell is going to release insulin. Okay, insulin. So insulin is secreted, and that insulin make your body, like your muscle or your adipose tissue, consume glucose. So glucose is going to be consumed by your body. If the glucose in your blood is too excess, and if it's beyond to your body consumption, it should be stored in the liver, and that's called glycogenesis. That means glucose is going to convert into glycogen and stored in the liver. That's called glycogenesis. So these are, so that when glucose is stored in the liver, or when glucose is consumed by your body, then the blood glucose level gets less or return back into the normal. So this is how homeostasis tries to maintain, for instance, the constancy of blood glucose level. But if the blood glucose level is reduced, another cells in the same gland detect a reduction of the blood glucose level, and these are the alpha cells. Okay, not the beta cells. So alpha cells now produce glucagon, not insulin. Okay, so glucagon is another hormone. So this glucagon antagonizes the effect of insulin, or they do have opposite effect, because insulin reduces the blood glucose level and glucagon increases the blood glucose level. So they have opposite effect, and that's called antagonistic effect. So the glucagon make the liver to break down glycogen into glucose, and glucose is get released from the liver into the blood, so that our blood glucose level is increased. Or glucagon make your body to consume less glucose in such a way that your blood glucose level is increased or return back into the normal. So this is really shows the three components of our homeostasis control system: the sensors, the integrators, and the effectors. And you should know that the function of each component, the function of the sensors, the function of the detectors, sensors, detectors, and receptors, the same. Okay, the same. But you should know the function of integrators, or you can say comparators, and the effectors. Then, when we discussed about the blood glucose control system, it is good to see what is glycemic index of a diet. So glycemic index is amount of carbohydrate found in each diet we are consumed every day. For instance, you may have bread in your breakfast. So one of the diets is bread, or rice, or potato, or banana, whatever it is. So it is good to know the amount of glucose in each food item or each diet. That's called glycemic index. Amount of glucose found in the blood. Found in the diet. Or you can say amount of glucose increase in the blood following a meal. To which extent the blood glucose level is increased following your banana, for instance. After you take the banana, after you take like the peanut pills, after you take the vegetables. Okay, so it is a percentage. It is a percentage. It is amount. It is number. Okay, so carbohydrates in each diet. Okay, for instance, there is carbohydrates in bread, and how much is that? So amount of carbohydrate or glucose in a diet divided by the pure glucose times 100 is the glycemic index. Okay, the glycemic index. So it estimates how much a person's blood glucose level increased following a meal. So carbohydrate or diet, absorbed highly in your GI or in your gastrointestinal tract, increase the blood glucose level high. Okay, so any diet, I mean that any diet rich in carbohydrate, okay, any diet rich in carbohydrate has high glycemic index, or any meal or any diet contain carbohydrates that can be absorbed easily in the GI that have high glycemic index. Okay, high glycemic index. So food with high glycemic index are rapidly digested, okay, rapidly absorbed, and increase in the blood, so increase glucose in the blood quickly. And these diets are not good for a patient with diabetes mellitus. Okay, so a patient with diabetes mellitus should take diet with low glycemic index. Okay, so it is good to list down or classified diet based on their glycemic index. Okay, so like for instance, you can have diet with like the vegetables, fruits, raw carrot, and so on. So these are important for a patient with diabetes mellitus because they do have low glycemic index. They do not increase the blood glucose level, okay, highly. So a patient with diabetes mellitus is recommended to check a diet with low glycemic index, like the vegetables, the fruits, okay, raw carrots. Otherwise, you can have food or diet with medium glycemic index, okay, medium glycemic index, like the banana, okay, or raw pineapples, oats, the cereals, and so on contain medium glycemic index, or they increase the blood glucose level, okay, a bit higher than diet with low glycemic index and a bit less than diet with high glycemic index. Otherwise, if you see rice, the bread, potatoes, and so on, they increase the blood glucose level quickly and highly. So they are called diet with high glycemic index. So diet or food or meal with high glycemic index increase the blood glucose level quickly, okay, and strongly, so that they are not recommended for diabetic patients. Okay, so it is good for you to have some concept about the glycemic index and blood glucose control system through homeostasis. Then there is homeostasis control system. Okay, we have said that homeostasis is physiological adjustment that tries to maintain the constancy of the values in the body, and in order to homeostasis to maintain that constancy, it needs components like sensors, integrators, and comparators. That is not enough. That's not enough. For instance, in order to write your name, you may need pen and paper. Okay, that may be the component you need to write your name. But that is not enough. In order to write your name, you should be able to write. Otherwise, even though you have pen and paper, if you don't, or if you are unable to write your name, you can't write. So homeostasis needs another thing, and that is ability to control the change, and this is called homeostasis control system. And you can classify the control system into intrinsic and extrinsic. Okay, intrinsic and extrinsic. So intrinsic means inside. Okay, intrinsic means inside. So there is process at the cell level or inside our cell that tries to maintain the constancy of the cell environment. Okay, look this figure 3. Look this protein, the green the green color protein found in the cell membrane, okay? And that is called sodium-potassium pump, okay? Sodium-potassium pump. This is a pump, okay, through which three sodium ions leave out the cell with an exchange of 2 potassium ions into the cell. So it is called sodium-potassium exchanger, or it's called sodium-potassium pump, okay? So what this pump is going to do? Assume there is more water inside the cell, okay? There is more water inside the cell. And if there is more water inside the cell, that may break the cell. The cell is going to bulge it, and that may facilitate breaking of the cell. So the cell will die. If the cell will die, no more function. Okay, that results in certain disease. So when the amount of water inside the cell is increased, then this pump is get active, so that 3 sodium leave out the cell into extracellular environment, okay, and 2 potassium enter into the cell. So the cell is losing 1 cation because the net is 1. 3 sodium leave, 2 potassium enter. So the cell is losing one cation. Okay. So if you have a number of sodium-potassium pump on in the cell membrane, the cell is losing more cations. So more sodium is leave out the cell than potassium enter into the cell. And you should know that sodium has osmotic effect. That means sodium has an ability to attract water. So water follows the direction of sodium. So when sodium leaves the cell, water leave out the cell. So when sodium leaves the cell and when water follows the direction of sodium, then amount of water inside the cell is going to reduce. Okay, because water get out from the cell. So this is called autoregulation, an intrinsic process made at a given cell. So this is an example. We can mention some other examples, but it is enough for the time. So at least you should know that there is an intrinsic homeostasis control system made at cellular level, like the sodium-potassium pump. Okay. Then you can have extrinsic one. Extrinsic, when you say extrinsic, when the control system is get from outside. Okay, like for instance, if the hormone secretion, like for instance, you can have the thyroid gland in your neck, and that thyroid gland may produce the thyroid hormone, and if that thyroid hormone secretion is controlled by the brain, it is called extrinsic. Okay, it's called extrinsic. So in the extrinsic homeostasis control system, there are two mechanisms. Okay, two mechanisms. Hello. So in the case of extrinsic, you can have the feed-forward control system and the feedback control system. Feed-forward and feedback. So in the case of feed-forward, the homeostasis control system is established before change is made. Like for instance, your salivary gland is stimulated and secrete hormone before you are going to check the food. For instance, if you are looking at food or meal in front of you, you salivate. Okay, that's called feed forward. The change is made in your body before we are going to check before the change is made. So it is a kind of anticipation. The brain is anticipate, or the brain is expect you are going to take that meal. That is why you salivate while you are looking at a meal, or even when you smell a food. Okay, you salivate. Saliva secretion is increased. Or another example, like for instance, when you get into a cold shower, the blood vessel or the arteries that supply blood into the surface are going to constrict, okay, before your body temperature is reduced. Okay, it's reduced. That's called feed forward. Okay, that's called the feed forward. The other is the feedback. So the name by itself indicates in the case of feedback, the homeostasis control system is established after the change is made. If your body tries to reduce your body temperature after your body temperature has been increased or reduced, that's called feedback after the change is made. Okay, after the change is made. Okay, or if your body tries to reduce the blood glucose level after your blood glucose level is increased, that's called feedback. So in the case of feedback, the homeostasis control system is established or starts after the change is made. So in the case of feedback, there are two control systems. So the first is the negative feedback control system. Okay, the negative feedback control system, and the other is a positive feedback. So in the case of negative feedback control system, the stimulus or assume there is change, and that change is reversed. That means, for instance, if your body temperature is increased, it should be reduced back. So that's called reverse. So the stimulus that brings a change is going to reverse it, is going to oppose it. Okay? In such a way that the stimulus that brings a change, okay, and the response from your body have opposite direction. That means if your body temperature was increased and if it turned back, then there is opposite direction. Then the change is made smaller. Look, for instance, your body temperature is normally 37 degrees centigrade. This is normal. But because of the changing factors, like for instance, it can be for infection, for instance, your body temperature is increased to 39 degrees centigrade. So how much is the change? How much is the change? Your body temperature is increased from 37 degrees centigrade to 39. So the change is 2 degrees centigrade. Then the negative feedback homeostasis control system return back your body temperature into like 37.6. So how much is the change now? The change is 0.6 degrees centigrade. So in the case of negative feedback control system, the change is made what? Smaller, because the stimulus that bring a change and the response made in our body have opposite direction. And this negative feedback homeostasis control system leads to compensate the loss. That means when there is loss, and that when there is change, okay, that change is returned back into the normal. So it is very important for our body, so that our body mostly used the negative feedback control system, okay, in order to maintain the well-being, okay, in order to have, in order not to have a disease, the negative feedback control system is very important. Look at this negative feedback control system. So assume there is factor normal, or normal value, your body, like 37 degrees centigrade, your body temperature, normal. Factor normal, okay? Then if you are exposed like into the cold environment, okay, your body temperature is going to reduce. Factor decrease, that means that your body temperature gets less. That should be detected, okay, by receptors or the integrators, okay. Then the receptors or the integrators send a message into the comparator, and the comparator compare, okay, the set point or the normal value with the changed value. Then appropriate response is made in the effectors. The effectors are structures in the body where response is made, okay. Then correction is made, and your body temperature is returned back into the normal, okay. So in this case, the stimulus that bring a change and the response made or the corrective response made from your body have opposite direction. That is why the change made smaller. In the case of negative feedback homeostasis control system. So what are the parameters in our body regulated by the negative feedback control system, or examples of negative feedback control system? So the first is the blood sugar regulation. Okay, blood sugar regulation. The first. Okay, we'll see that one. Osmo regulation. What does we'll see. At least you should list down the parameters in the body. Those can be regulated with the negative feedback control system. Okay. So the other is, so the blood sugar level is the first. So osmoregulation is the other. The control of body temperature, or body temperature is another parameter in the body regulated by the negative feedback homeostasis control system. The blood carbon dioxide and the pH regulation. Okay, regulation of blood volume and pressure, endocrine gland secretion, regulation of acute hemorrhage, which is that one actually, end product inhibition, and synaptic inhibition. So these are list of parameters in the body regulated by the negative feedback homeostasis control system. So you should know that. For instance, if you are going to ask it, which of the following parameters in the body regulated by the negative feedback homeostasis control system, you should list it down. Okay. Okay. Look how our blood glucose is regulated. Actually, we discussed earlier. Okay. So I'm going to repeat it, what we discussed in the earlier slides. Okay. So assume there is imbalance in your blood glucose level. That said that your normal blood glucose level is ranging from 70 to 120 milligram in deciliter of blood. That's the normal. So assume your blood glucose level is increased. Okay, your blood glucose level is increased, so there is imbalance. Okay, there is imbalance. So when your blood glucose level is increased, then that should be detected by the beta cell of the pancreatic gland, so that insulin is produced, and that insulin made your body to consume the increase in the blood glucose level. Or if glucose in the blood is too excess beyond your body consumption, it should be converted into glycogen and stored in the liver, and that's called glycogenesis. So these are two ways, okay, your homeostasis reduce the blood glucose level if your blood glucose level is increased following a meal. For instance, if you have, or if you had like breakfast, bread at your breakfast, then after 20 minutes, your blood glucose level is increased. But after 2 hours, it returned back into the normal, because the bread you had increased the blood glucose level, and that blood glucose level, or that blood glucose was consumed by your body, so that it gets back into the normal. Otherwise, when your blood glucose level is reduced, like for instance, if you don't, if you don't, if you skip your breakfast, or dinner, whatever it is, that if you didn't take meal, that means your blood glucose level is going to reduce. And finally, you may have shock. Even if your homeostasis failed to compensate the loss, you'll have shock. Okay, hypoglycemic shock. Hypo is less. Hypoglycemic shock. So then the alpha cell, not the beta cell. Okay, the beta cell produce insulin, but now the alpha cell produce a glucagon, and that glucagon antagonizes the effect of insulin, so that glucagon increase the blood glucose level. So how? Because glucagon make your liver to release the glucose quite stored before. Okay, then that glucose is released into the blood, and your blood glucose level is increased. Then our homeostasis is normal. Okay, mainly the blood glucose level. So this is not positive feedback. This is the negative feedback. Okay, the negative feedback homeostasis control system. The other is osmolarity, amount of solute per kilogram of solution is osmolarity. Okay, so how that is regulated? The normal is around 300 milliequivalent per liter of blood is the normal osmolarity. Okay, then assume your osmolarity is increased. Okay, increase osmolarity. So when your osmolarity is increased, there should be changes in your body. Like for instance, if you take salt, okay, እየወጣችሁ ያላችሁ ልጆች አትውጡ እያዩዋችሁ ነው እሺ so for instance if you take salt or diet with more sodium that you feel like you feel to take water, okay, you feel thirst, okay, why your osmolarity is increased because of solute like sodium or whatever it is. Then the following four processes are there, okay, four processes. Four processes. Okay, so the first is increase natriuresis. You know, natriuresis is excretion of sodium. Sodium is natrium. Okay, when you write sodium, Na, that's natrium. So natrium is sodium. So natriuresis is increased excretion of sodium in urine. So when sodium in the blood is high, then your kidney check that sodium and removed in the form of urine. Sodium excretion is increased, and that's called natriuresis. One response from your body, one negative feedback process in your body to reduce sodium in the blood. Okay, the next is reduce sodium appetite. That you are not, if your appetite is reduced, down row is reduction, it shows reduction. So you are not going to take more salt. So salt consumption is stopped. Okay, the other is increase thirst. Okay, thirst. The thirst. That you feel to take water. Then you are going to take water. Okay, and blood is going to dilute it. Okay, blood is going to dilute it. Then these are some of the processes that return your sodium back into the set point. It says the set point. Set point is the normal. That the normal amount of sodium is from 35 to 145 milliequivalent per liter. That you should know the normal value initially, so that you can say this is high or this is low. So the normal sodium is ranged from 35 to 145 milliequivalent, okay, per liter of solution. Okay, so all these processes make all these processes make sodium level in the blood back into the set point or back into the normal. Otherwise, when sodium in the blood is reduced, that's called hypotonicity. Hyper is high. Hypertonicity is when sodium is high in your blood. Hypotonicity is when sodium is less in the blood. So when sodium gets less in the blood because of so many factors, okay, opposite response should be made in your body if you are normal, if you are healthy, or a man with homostasis. Okay, so the first is reduced natriuresis. So less sodium, okay, less sodium removed from your body in the form of urine. Okay, reduction in natriuresis. Okay, the other is increased sodium appetite. So you are going to take salt, for instance. Okay, the other is reduced thirst. First, and you don't feel, okay, you don't feel to take water, so you are not going to take water. No water intake. Okay, so if you are not going to take water, you are not going to dilute your blood. So sodium concentration is going to increase. The other is there is what called vasopressin. Vasopressin is hormone, or it's called anti-diuretic hormone. You should know that. Vasopressin is anti-diuretic hormone. Why it's called vasopressin? Because it narrow or constrict the blood vessel through which blood is flow in your body. Since it constricts the blood vessel or narrows the blood vessel, it's called vasopressin. Or since it reduced excretion of water, it's called anti-diuretic hormone. So when sodium in your blood is reduced, okay, then vasopressin secretion should be get less, so that more water is get out from your body in the form of urine, so that sodium concentration is increased. So this is called osmoregulation, an example of negative feedback homeostasis control system. Okay, another example, another example. The next is thermo regulation, how your body temperature is regulated. Actually, your body temperature should be maintained around 37 degrees centigrade, but there are so many factors that increase or reduce your body temperature. Okay, so when your body temperature is increased or reduced, it should be returned back into the normal. How? Because of the process in your body. Look how your body regulates your body temperature. So in order to your body regulates the body temperature, the increase or the increase or reduction in your body temperature should be detected by detectors, or these are called thermoreceptors. So the thermoreceptors are found in your skin, for instance, in your skin, or the thermoreceptors can be found inside your body, like on the wall of your blood vessel, and so on. So assume your body temperature is reduced. Sorry, your body temperature is reduced. So when your body temperature, let us start assume your body temperature is increased. So when your body temperature increase, then that's detected by the thermoreceptor in your skin, or the thermoreceptor found on the wall of the blood vessel. After they detect, okay, the increase in your body temperature, then they send message into the brain. I think you are looking at a circle in your brain, the yellow circle. That's called thermostat center. Thermostat center. The center in the brain detects your body temperature, okay, because of the receptors. Or you can say thermoregulatory center or thermostat center. That is found in hypothalamus. Hypothalamus is root-like structure in your brain that contains the thermoreceptor. So that thermoreceptor divided into areas. The first is pre-optic area that contain heat-sensitive cells. The cells, those become very active when your body temperature is increased, heat-sensitive cells. Then, when the heat-sensitive cells get active, then heat-losing processes are made in your body. One is sweating. Then sweating is cooling your body temperature, is cooling your body. So one of the heat losing process is sweating. Sweating. Two, dilate the artery or artery supply blood into the surface of your body. Vasodilation of arteries. Second, okay, heat losing process. Reduction of metabolism, glucose breakdown in your body or fat breakdown in your body reduced. Third, heat losing process. You should take notes. Okay. The fourth is salivation. You salivate more. Okay, and you draw out your saliva. You are cooling. So these are the heat losing responses. when your body temperature is increased, and that was detected by receptor in the pre-optic area of your hypothalamus. The next is when your body temperature is gets less, like if you are exposed into a cold environment, okay, or whatever the changing factor, assume your body temperature is reduced. Okay, so when your body temperature reduced, that's detected by posterior hypothalamus that contain cold sensitive cells. The cells, those become active when your body temperature is reduced. When your body temperature is reduced, okay. Then when your body temperature gets less, then the response should be heat gaining mechanism. One is shivering. You shiver. For instance, if you get into the cold shower, there is shivering. That is very important. That increases your body temperature. Shivering is contraction of the skeletal muscle. So shivering is very important. Okay, shivering. One. The other is constriction or narrowing of arteries supply blood into your skin. Third, increase metabolic activity. Your appetite is increased, glucose or fat breakdown is increased, heat is generated. Okay, heat is generated. So these are some of the heat gaining process when your body temperature is reduced, and that's detected by the posterior hypothalamus that contains the cold sensitive cells. Okay, but this center affected by infection. When you have infection, okay, like that can be like the coronavirus or whatever the infectious agent, assume you get infected. Then pyrogens are produced. Pyrogens are proteins produced by the infectious agents in your body, and that pyrogens affect the set point of your body temperature. The set point of your body temperature is 37. The brain knows that your body temperature is 37. Now the set point is get high, like into 38. Then even though your body temperature is high, still you have shiver when you have infection, for instance. Okay, and that is called heterostasis. Heterostasis, not homeo. Heterostasis is different from homeostasis. Heterostasis is maintaining organism at a changed parameter. So increase your body temperature during infection is important sometimes because it can affect the infectious agents. But if the body temperature is increased too much, that is very severe. So we should have kind of treatment to control that increase the body temperature. So thermoregulation is another negative feedback homeostasis control system. Blood pressure regulation. Okay, blood pressure regulation. Like your blood pressure is 120 by 80 millimeter of mercury is normal, but sometimes your body temperature, your blood pressure may increase or reduce. Then there should be process in the body, okay, that regulates your body temperature at different time. So the first is called short-term blood pressure regulation. Your body regulates your blood pressure very quickly at a fraction of time. Like for instance, assume your blood pressure is increased, okay, than the normal. That is detected by the baroreceptor. You know baroreceptors, receptors that detect pressure, and those baroreceptors are found in aortic arc or carotid sinus. Then the message gets into the brain, mainly to the cardiovascular center in the brain, that is in the medulla oblongata. Then there is integration there, and command is made, and that command is get into your heart, so that your heart rate is reduced, and your blood vessel is going to dilate, so that your blood pressure is reduced if it was increased, because blood pressure is equals to heart rate times stroke volume times resistance. Okay, so actually you'll discuss this one in your cardiovascular system. We are talking about the introduction. A bit may be difficult for you to understand this one, but when you when you are going to take more courses in the physiology, things become very, very clear. But at least for the time, you should know that there are variables in the body regulated by the negative feedback homeostasis control system, like blood glucose level, temperature, sodium, blood pressure. So that blood pressure can be regulated either with a short period of time or intermediate time. I mean that your body needs some time to regulate your blood pressure. Like this is called intermediate term blood pressure regulation. Like the first is capillary fluid shift. That means when your blood volume is increased, then fluid leaves out from your blood vessel into the tissue. So the amount of blood in the blood vessel is reduced, and the force exerted on the wall of the blood vessel is get less. That is called capillary fluid shift. There is fluid exchange between your tissue and capillary. Capillary is the smallest artery in your body where materials are exchanged between the blood and the tissue. So the first is this one. The other is stress relaxation. I mean that when your blood pressure is increased, blood pressure is force exerted on your blood vessel by blood. So assume your blood pressure is increased. Then when your blood pressure increase, your blood vessel is going to extend it, stretching. Then the luminal diameter increase. Okay, so that the force exerted on the whole of the blood vessel is reduced. Okay, that's called stress relaxation. The last is long-term blood pressure regulation. Okay, your blood pressure can be regulated, but that takes more time, even 2 weeks or more than that. So in this case, there is what called RAS, renin, angiotensin aldosterone system, renin, RAS, renin, angiotensin aldosterone system. Okay, look this system. Okay, so in order to discuss about homeostasis, mainly the feedbacks, assume there is change. Okay, assume there is change. Okay, assume there is change. So assume your blood pressure is reduced. Okay, look the figure 10. Look the figure 10, and you'll see. I think you'll see the kidney at the left. Okay, sorry, at the right, kidney. So assume your blood pressure is reduced. Then renal blood flow or amount of blood flow into the kidney is reduced. Then renin is produced. Renin is a hormone, or you can say chemical, produced from your kidney, and that renin is released in the blood. Okay, and then you can have liver that produces angiotensinogen. The angiotensinogen is a protein made in your liver. Okay, made in your liver. Then that angiotensinogen is converted into angiotensin 1 by renin from your kidney. Okay, from your kidney. Then angiotensin 1 is converted into angiotensin 2 by angiotensin converting enzyme, ACE, angiotensin converting enzyme. This enzyme is produced from the pulmonary capillary found in your lung. Then angiotensin 2 is get into your adrenal gland. This gland is found at the top of your kidney, so that aldosterone is produced, and that aldosterone, okay, reduced sodium excretion below the kidney, sodium excretion or reduced water excretion, so that your blood volume is increased and your blood pressure now is increased. It was reduced, now increased. So the response and the stimulus have opposite direction, so the change made smaller. Or angiotensin 2 is getting to the kidney, so that excretion of sodium and excretion of water is get less, so that your blood volume is reduced and your blood pressure is increased or returned back into the normal. And this is called the RAS system. Okay, and it takes few times, so that it's called long-term blood pressure regulation. Okay, unlike that of the short term, that needs a fraction of time or a small time. The other is a regulation of calcium. Okay, calcium. That your body needs calcium, and that calcium should be maintained constant, and that's called the calcium regulation. So, what are the components involved in the calcium regulation? Okay, so look, so we should assume your calcium is get high or it get less. Because there should be a kind of assumption. So assume your blood calcium is rising or your blood calcium is increased. So there is imbalance. I mean that if the calcium in your body is increased, that's imbalance. So homeostasis tries to maintain that imbalance or return back a bit into the normal. Okay. Then how? Look, we need detector, one of the components, okay, or the sensor, and that sensor that sense the increase in the blood calcium is found like in your thyroid gland. So there are follicular cells in your thyroid gland that detect increase the calcium in the blood. Then the follicular cells in your thyroid gland is going to produce calcitonin. Okay. Okay, then that calcitonin activates like osteoblast cell in your bone. So that, or osteoblast, the bone formation cells. So osteoblasts make your bone to take calcium from the blood. So now calcium is going to reduce it. Okay, okay, or return back into the normal. Otherwise, when the calcium in your blood is reduced, then there is something different process. So the same thyroid gland is going to detect reduction of the calcium in your blood, but it is not calcitonin now that is produced from the thyroid gland, but it is the parathyroid hormone. Then the parathyroid hormone antagonizes the effect of calcitonin because these two hormones are called antagonistic hormones. They induce opposite response from your body. So if if calcitonin reduced blood calcium, then parathyroid hormone increase the blood calcium, so that the parathyroid hormone activates osteoclast cells, not osteoblast, osteoclast. Okay, so osteoclast cells facilitate demineralization of your bone in such a way that your bone is going to facilitate to release the calcium into the blood, so that the blood calcium is going to increase or back into the normal. Otherwise, the normal is the normal level of calcium, because the free calcium and protein bound calcium is ranged from 9 to 11 milligram in a deciliter of blood. That's the normal. If you don't know the normal, it may be difficult to say this is high or low. So we are expected to know the normal value of the parameters in our body. Mainly in physiology, should know the normal value, so that you can say this is high or this is low, and that's called the deviated of the change value. So the body tries to that return back into the normal. The other is sodium regulation. Actually, you have seen this one earlier, but it is good what components are involved in sodium regulation. So we should know the normal value initially. How much is sodium outside the cell, inside the cell? So the normal is ranged from 35 into 145 milliequivalent in a liter of blood. That's the normal. But since we are exposed for the changing factors that come internal or external, this value is not static, rather it's dynamic. That's why homeostasis is called dynamic equilibrium. It tries to regulate. So the first is aldosterone. So aldosterone increase the blood sodium level. So aldosterone should be produced when your sodium in the blood is get less. Okay. The other is the RAS system, renin-angiotensin aldosterone system is involved, or this is another component. okay, and the other is antidiuretic hormone, or sometimes called vasopressin, and okay, enlarged vasopressin or AVP, or atrial natriuretic peptide, atrial natriuretic peptide, the peptide from your heart, from the atrium, that facilitates natriuresis or excretion of sodium. So sodium excretion, or that's called natriuresis, is increased when sodium in your blood is get less. Okay, so in such a way that your sodium in your blood is regulated. So at least you should know that the components, should list down the components involved in sodium homeostasis or in regulation of your sodium. Okay, so you should know the effect of these components again. So this is all about the negative feedback homeostasis control system. So the next is the positive feedback homeostasis control system. So there is difference, okay? So in the case of positive feedback homeostasis control system, the stimulus that bring a change is going to intensify. Or that once there is a change in your body, like for instance, once there is severe bleeding in your body, that bleeding is facilitated. Or once blood clotting is initiated, that clotting is facilitated gradually. In the case of positive feedback homeostasis control system. So the initial stimulus is going to intensify or facilitate, unlike that of negative one, in such a way that the stimulus that brings the change is reversed or opposed. Okay. So the positive feedback homeostasis control system leads to the change in the same direction, or that means the stimulus that bring a change and the response have the same direction, unlike that of the negative one. So if the stimulus that bring a change and the response made in your body have the same direction, the change is made greater. Once there is clotting, that clotting is gradually increase, and so on. Okay, so the change is made greater. But in the case of negative feedback homeostasis control system, since the stimulus that bring a change and the response have opposite direction, the change is made smaller. Okay, so the output now, in the case of positive feedback, output not return back into the normal. Okay, so has less physiological advantage, because sometimes, not always, result in decompensation or result in some problems. Okay, so it has a disadvantage. Actually, we'll see some of examples in the positive feedback. So you'll see which of process in the positive feedback are very important for the body or not important. We'll see that one anyways. Okay. So these are examples of the positive feedback homeostasis control system. So the first is the pumping effect of heart following severe bleeding. What would happen, okay, in your heart after severe bleeding? For instance, if you bleed more than 1.5 liter of blood, that's severe. So what would happen in your heart? Which is that one? Uterine contraction during labor. When a mother gives a birth, the uterus should be contracted and the fetus should push down into the cervix, and the cervix should be stretched, and mechanoreceptor should detect that stretching process. We'll see that one again. Blood clotting process, luteinizing hormone surge during ovulation. You know, ovulation is a process through which matured ovum is released from ovary of the female. That's called ovulation, and surge is increased. So a few times before ovulation, or a few times before matured ovum is going to release from the matured Graafian follicle, luteinizing hormone in your blood should maximum, and that's called luteinizing hormone surge, and that is through positive feedback homeostasis control system. The other is excitable cell depolarization. Actually, you will see this one, or actually you'll see depolarization process or excitable tissue in module 1 or part 2. Okay, and that after this module, I mean that hypertensive nephropathy, and that when your blood pressure is increased, and if that is not controlled, okay, then the microscopic structures in the kidney, which are called the nephrons, are going to injure, and that's called hypertensive nephropathy. So if one of the nephrons is injured, then the load on the remaining is get high. So the other nephrons are going to be injured, and that's called hypertensive nephropathy. Okay, so this is example of positive feedback, and that is disadvantage. End product facilitation. End product facilitation. I mean that, for instance, there are a number of reactions in your body. So, like for instance, A plus B. Okay, so this can be reactant. Then you'll have the end products. So if the end product facilitates the enzyme, facilitates the reaction, that's called end product facilitation. But still there is end product inhibition. That is negative feedback. Okay, presynaptic facilitation and calcium-induced calcium releasing mechanism in your cardiovascular system or in your heart. You see actually this one in some other module. Anyways, these are some of examples in the positive feedback homeostasis control system. Okay, look for instance, why a subject with a severe bleeding is going to die through a positive feedback homeostasis control system. So assume there is a man or a woman, or there is a subject with severe bleeding, like the subject has lost like 2 liters of blood. Okay, then what would happen on the pumping effect of your heart or the pumping effect of this subject, okay, with severe bleeding? Okay, so normally we have said that amount of blood circulated in your blood vessel, or that's called the cardiac output, is 5 liters. Okay, so when 5 liters of blood is pumped from your heart in 1 minute, then some of that blood is returned back into your heart. Okay, but if the subject is losing 2 liters, then amount of blood returned back into the heart is 3. Okay, 3 liters. Then the cardiac output is now reduced. So the amount of blood get back into the heart together with oxygen and nutrient is reduced. So the pumping effect of the heart is reduced gradually. Okay, the pumping effect of the heart is reduced gradually. The beat is going to reduce. In the case of negative feedback, and the subject will die. But if the negative feedback overrides than the positive one, the subject is going to survive. That means, for instance, if the heart rate is going to increase following bleeding, that's very important. That's very important. That process is try to save that subject. But if the beat is get less gradually, it is the positive feedback overrides than the negative feedback, and that's very dangerous. Okay, so this is disadvantage. One disadvantage. Look figure 13. That uterine contraction during labor. Okay, so assume there is uterine contraction that is initiated by estrogen. Okay, there is hormone here, and this estrogen is from the ovary of the female, and that initiates uterine contraction. Okay, so the middle part of the uterine will contain muscle, and that muscle is going to contract. Then the fetus in the womb is going to push down to the cervix, and the cervix is going to relax it, and that relaxation is detected by the sensor, one of the components in our homeostasis control system, and these are stress receptor. Okay, then the message is get into the brain, so that oxytocin is going to release from posterior pituitary gland, and that oxytocin potentiates uterine contraction. So uterus is going to contract more. So the frequency and the intensity of uterine contraction is increased gradually until the mother give a birth. Okay, so this is advantage of the positive feedback homeostasis control system. So uterine contraction during labor or in order to a mother to give a birth is because of the positive feedback homeostasis control system in the mother. If this is failed, like for instance, if oxytocin is not released and potentiate uterine contraction, normal delivery process may be tough. Okay, maybe tough, maybe difficult. Okay, otherwise, still the prostaglandin increase the uterine contraction. Okay, potentiate the delivery. Okay, so this is advantage. Okay, advantage of the positive feedback homeostasis control system. Okay, this is utilizing hormone surge during ovulation. Okay, so this is what we discussed in the earlier slide. So at least you should know that few times before ovulation or few times before a woman is going to release matured ovum to be fertilized with a male gamete, luteinizing hormone in the blood should be maximum. Otherwise, the follicles that surround the ovum is not going to rupture and no ovulation at all. So luteinizing hormone surge or increase in the blood is very important. Okay, for a mother to ovulate the ovum, and if there is gamete waiting for that ovum or that egg, then fertilization may be possible. It depends on actually. Okay, so this is called luteinizing hormone surge during ovulation or 2 times before ovulation. Again, positive. So the increase, I mean that the increase luteinizing hormone in the blood 2 times before ovulation is through positive feedback homeostasis control system. So this is advantage. Okay, this is advantage. Depolarization or the reduction of the polarity of the cell in your muscle cells or in your nerve cell is because of the positive feedback. Actually, you'll see this one. Anyways, when the cell in your body is found at rest, the net charge inside is negative and the net charge outside is positive. That is called polarity. Okay, but when you apply the stimulus and if the cation channel open, like if the sodium channel open, sodium enters the cell and the inside becomes positive, that's called depolarization. And once that depolarization is started, or once a single sodium enters into the cell, more sodium, okay, ions are going to enter into the cell. So the inside become more, more positive. That's called depolarization process through positive feedback homeostasis control system. Again, another advantage. Okay, another advantage of the positive feedback homeostasis control system. The other is blood clotting process. Look this figure again. How platelets are going to be activated on the ruptured area, okay, in your blood. So look, this is your blood vessel, and your blood vessel is ruptured, okay, because of so many factors. Like for instance, it can be mechanical. Okay, you rupture your blood vessel, then there is bleeding. Okay, blood get out from the circulation, bleeding. But after some times, you are looking at, okay, clot that seal or close the opening. So don't remove that one because it tries to stop bleeding. Otherwise, if you remove the clotted blood mass in the opening area that tries to close the opening, you reinitiate bleeding. Okay, so don't touch that one. So how platelets are going to aggregate on the ruptured area? Those try to seal or close the opening, and further bleeding is stopped. That's homeostasis. If this homeostasis fail, there may be adaptation, okay, or there may kind of treatment. You may tie the ruptured area, or there are so many process, but those are not homeostasis. Homeostasis is the physiological process in the body. Okay, you are not doing that actually. So assume when your blood vessel is ruptured, then endothelial cells are exposed and collagens are exposed actually into the blood. Then chemotactants are produced. Okay, then a single platelet is going to attract, and single platelet is get into the ruptured area. Then that platelet get active and it releases so many factors. Then another platelet is going to attract and attach it on the ruptured area. In this way, platelets are aggregated on the ruptured area. That's called platelet aggregation. And that aggregation should be stabilized by fibrin protein, and that's called clotting. So this clotting in the ruptured area try to prevent bleeding. So it is advantage. But sometimes clot may be created in the circulation. Okay, so if clots or if clotted blood mass are created in your circulation, that mass occlude the blood vessels that supply blood into your organ, like into the heart or into the lung. That is disadvantage. That's called thrombosis. That is abnormal. Okay, otherwise clotted blood mass in the ruptured area and that tries to stop bleeding, and that is advantage. Okay, advantage of positive feedback homeostasis control system. Then there is what called gain of homeostasis. Gain. To which extent, I mean that to which extent our homeostasis tries to maintain constancy. Okay, that's not 100%. Okay, assume, for instance, your blood pressure was, I mean that 100 and increased to like 175 millimeter of mercury. Okay, so there is increase in your blood pressure by 75 millimeter of mercury, and that should be detected by the sensor, one of the components in the homeostasis control system. And these are the baroreceptors. Those are found either in the aortic arc or carotid sinus. They detect that one. Okay. Okay. So when they detect, and when the process is made, like we mentioned in the earlier slides, then your blood pressure return back into 125 from 175. So the change is made what? Smaller. But still there is error. Okay? So the baroreceptor system corrects by 15. Minus shows reduction. So still there is error by 25 millimeter mercury. So gain of homeostasis is correction divided by error. Okay, and you should know that our gain of homeostasis is affected by age. That means when you get aged, our homeostasis is reduced, so that the probability to have different diseases is increased. Okay, so other factors are different diseases. Okay, affect the component of the homeostasis control system again, and that affect the gain of our homeostasis. So you should know that the gain of homeostasis is not static, rather it is dynamic. That means our gain of homeostasis is affected by so many factors. One is age, the disease, okay, and the lifestyle, the way we are living, okay, or the diet we are consuming, and so on, can be taken as some of the factors that affect the gain of homeostasis. So that you should know that our gain of homeostasis is not static, rather is dynamic. It can be affected by so many factors. Okay. Then the other thing that is mainly related to this homeostasis is allostasis and adaptation. I'm not going to tell you detail about allostasis, okay, because this is another big concept, okay, maybe related to homeostasis. So there is adaptation, okay, you know, there is adaptation. So adaptation is gradual process made as to adapt the change, okay, adapt the change. So process, that's gradual process, make us to adapt the new demand, okay. So during that process, structural and functional changes are made. So those structural and functional changes made in our body can be positive, and those increase our fitness for and that environment may need new demands because the bioavailability of oxygen in that environment is a bit less, so that there should be process in the body, or there should be structural and functional change made in the body. So if the change made is positive, that makes us to adapt the environment. That's called fitness. But if the change is mal, that means if the change is wrong, okay, or if the change, both structural and functional change, is negative, then that reduces our fitness to the environment. For instance, if you get into the higher altitude, and if you developed the altitude sickness, like your appetite may be reduced, or there may be headache, vomiting, and so on. If your homeostasis unable to maintain that one, it is better to return back into the sleep. Otherwise, there may be other complication, and that's called altitude sickness. Or for instance, if you are exposed for stressor chronically, the hippocampus volume is going to reduce. That's called a kind of negative change, or that's called maladaptation. So ability to form memory is reduced by chronic stress. Okay, so chronic stress, or a subject with chronic stress may have problem in learning and memory. The other is cold-induced thyroid gland enlargement. I mean that people who are living in cold environment, they should adapt that cold environment so that the thyroid gland should be enlarged, so that more thyroid hormones should be produced. And the thyroid hormones are called thermogenic because they increase the body temperature. So if your body temperature is increased, you adapt that environment. Okay, that cold environment. Hot-induced sweat gland enlargement is another kind of adaptation made in your body, okay, to fulfill the new demand you are exposed, okay. The baroreceptor adaptation, but you know the baroreceptor adaptation, we have said that when your blood pressure is increased, baroreceptor should detect, okay. But sometimes, even though your blood pressure is increased, the baroreceptor in the carotid sinus or aortic arc may not detect, okay, or may not respond for the change in the blood pressure. That's called baroreceptor adaptation, and this is very wrong. I mean that your homostasis failed to detect or failed to make compensation on the increase in the blood pressure. That's called baroreceptor adaptation. Okay. Otherwise, as I tried to mention in the earlier slides, allostasis is maintaining through a change. There may be a condition. Okay. There may be a condition in the subject, okay, at which the changed value may be important, okay, like increase the body temperature during infection may be important, and that's called allostasis, or that's called heterostasis, not homostasis. Homostasis is maintaining at a constant value, but allostasis or heterostasis is maintaining at a changed value, okay. Okay, so we are talking about, or we are talking about the adaptation. So one of the adaptation is high altitude adaptation. Okay, one example. Okay, high altitude adaptation. So if we are exposed into the high altitude, then oxygen in that environment is less. Oxygen saturation or the blood saturation is get less, and that's called hypoxemia, or when the oxygen saturation in the blood is reduced. Okay, then what changes should made in the body so that we are going to adapt that high altitude? So the first is increase the ventilation rate. Okay, increase the breathing rate, or increase the ventilation rate, or amount of, or sorry, the number of breaths per minute is going to increase. Okay, one change in your body to adapt that higher altitude. The second is increase red blood cell count, and that takes some time, so it's called long-term process. Okay, increase the red blood cell count. Okay, the second change. For instance, if I'm going to ask you which of the following change is made in your body when you are exposed into the higher altitude, like Receptors in Ethiopia or Himalaya, whatever the higher altitude. Okay, you should list down what changes are made in your body during that condition so that you can adapt that environment. Otherwise, you are going to develop altitude sickness. Vomiting may be there. Okay, headache may be there. Loss of appetite may be there if these changes are not made in your body. Okay, so the next is peripheral chemoreceptor stimulation. I mean that there are chemoreceptors that detect gas like oxygen. Okay, those are found outside brain in the spinal cord. Okay, like in carotid, like in aortic arc, those are called peripheral chemoreceptors. Those are stimulated during that condition. Okay, plasma volume reduced and osmolarity increased. So water intake is get less. So if you are going to expose it into higher altitude, okay, you are not going to take more water. If you are going to take more water, you diluted the blood. So the concentration of red blood cell not increase. That's not good. So not take more water. So the physiology by itself make you, okay, not to take more water. A reduced tissue hemoglobin, HGB is hemoglobin, affinity to oxygen. I mean that hemoglobin is protein that carry oxygen, okay, from your lung into the tissue. Then when hemoglobin reaches the tissue, hemoglobin is expected to release oxygen into the tissue, okay, into the tissue. So if affinity of hemoglobin to oxygen is get less, more oxygen is going to released into the tissue. So these are some of the changes made in our body when we are exposed into the higher altitude, okay, into the higher altitude. Okay. The other is, if we are exposed into the higher altitude, in order to in order to adapt that altitude well, there should be gene expression alteration. So if you are exposed into the higher altitude, oxygen in the body get less, hypoxia. Then hypoxia inducing factors are produced, like HIF1, hypoxia inducing factor 1. This is called gene transcription control factor. Okay, so regulates genes for EPO. Okay, EPO is erythropoietin. Erythropoietin is protein produced in the kidney that increase red blood cell synthesis, or that vascular endothelial growth factors, VEGF, vascular endothelial growth factors. Okay, so hypoxia, the hypoxia facilitates the production of HIF, hypoxia-inducing factor. So this factor affects the gene. You are looking, figure 7 is the gene. This is the DNA actually. And you can have smaller molecules in the DNA, and those are called the genes. Okay, so you can have a number of genes. And those genes, okay, affected by hypoxia-inducing factor. So proteins are synthesized. So there are phenotypic changes. You know, changes you can see. It's called phenotypic change. Okay, observe it in people who are living in the higher altitude. Okay, so that's called higher altitude adaptation. So you should know that path changes are made. Okay, path changes are made in human being when these human beings are exposed into the higher altitude. Okay, into the higher altitude. Okay. Can we have some time rest? Please take. Yes. Can you have some time rest? Yes. Okay. Okay. Yes. Okay. 10 minutes. 10 minutes. Okay. Then we will return back. Okay. And we'll continue. So 10 minutes. Okay. You can left out for 10 minutes.
The constriction or arrows. This is a continuation of this morning lecture of the cell cycle. You have already started this morning, so I will continue with the remaining part of mitosis. Genetic material. Okay, so this is about cytokinesis. So how cellular membrane to division cytoplasm, and this is by forming constrictions. The cytoplasm is constricted of the cell, and through these contractile proteins known as actin and myosin contractile proteins. These are contractile proteins aligned along the equator of the cell that constriction of the this is a continuation of this morning lecture of the cell cycle. You have already started this morning. Plasm of the cell after completing along the cell, that's the nuclear membrane. The nuclear membrane in order to become very, and finally this creates cells with their own genetic material outside kinesis.